Equilibrium is a concept that's going to take up a lot of our learning over the next few weeks. And so we want to pay really close attention to what equilibrium means and how it affects our understanding of the kinetics of chemical relationships. First of all, equilibrium is denoted by a symbol that is different than the traditional arrow symbol that means yields in the chemical reaction. Notice we have arrows going in both directions. And what this means is that this symbol is acknowledging the fact is that chemical reactions are dynamic in nature, and the concentrations of chemical reactants and products are always in flux to some degree, even if we keep a fairly stable temperature and pressure in the conditions. What this means is even though we may be at what's called the finished point of a reaction, we're acknowledging that that doesn't mean that no chemical reactions are taking place. All that it means is that reactions are going on all the time in both different directions, but at an equal rate. So we have reactants turning into products at a net rate that products are also breaking back down into reactants. That is the closest thing to a steady state in the reaction that we will have. But we are never going to have a case where there is no chemical activity happening on a molecular level. So what happens when we are analyzing chemical reactions, we can look at it in terms of an equilibrium constant as a kind of a value that is a ratio of products to reactants. And this acts as a measure of the favorability of products being formed in this reaction under set conditions versus the reactants. So KEQs for short, equilibrium constants, are good metrics for helping predict the dynamics of a product to reactant ratio in a reaction. And so when we look at a KEQ, we can get a sense of how much of the reaction is really going to happen. If we have a large KEQ, we are going to be favoring more products than reactants. But if we have a low KEQ, then reactants are favored under those set conditions, and presumably the conditions would have to be changed if we wanted to favor products more. So the way that the KEQ is derived is that we take a reaction and we basically make a fraction of products over reactants with the molar concentrations of each substance that is involved in the reaction powered by their coefficients. So as we can see here, we have 2 molecules of A for every 1 molecule of B, and that is borne out with a powering of 2 for A and an implied 1 for B, whereas on the product side, we have 1 C for every 4 Ds, and then that 4 is represented as an exponent. And so by knowing the known concentrations, we can work out this constant. By knowing the constant, we can often predict how much of a certain combination of reactants will give an expected amount of products. So first we're going to work on simply deriving the KEQ. So let's say we have a reaction for this case, and it's happening at 400 Kelvin. And it has turned out that if we started out with these 2 concentrations of our reactants A and B, we got these concentrations of our products C and D. So we simply plug them into this formula here, and we got a product that is obviously not very favorable towards product. We have an answer that is more favorable to reactants. And this, of course, is borne out by the fact that stoichiometrically we have far less of our products than we do our reactants. So this comes as no surprise. So in sum, The KEQ is a way of measuring a kind of ratio of result to what we put into the equation. Ones that have large KEQ values have very favorable product results. Those that have low KEQ values favor reactants. In our next video, we'll discuss factors that affect whether reactants or products are favored and how that favoring can be changed.